So let's look at another way to define natural transformation as functors, which is related to a previous way we've seen in an interesting way. So going back to the definition of a natural transformation, we have a family of morphisms in D, alpha x, alpha y, indexed by the object of C, x, y, which has a very special property that given any morphism f in C, the corresponding square of joining the extremities which arise from transporting f through capital F or transporting f through capital G will commute. Now this commutation property, of course, it is very important and it arises everywhere, and one place where it arises is when we have a functor. When we have a functor, any functor, you draw some diagram in the initial category that it starts from. It will be transported to some diagram in the target category, and if the initial diagram commutes, then the target diagram will automatically commute. Since we are requiring this commutation property in D, it's tempting to try to build some category C prime that will already have this commuting diagram. Now, let's introduce this category 2, which has 2 objects and 1 morphism. And you might think of it as some kind of a time. So we have time 0 and we have time 1, and we can travel from time 0 to 1 and not from 1 to 0. And now let's consider C cross 2, which is like C through time. And the objects of C cross 2, which is a Cartesian product of category C and category 2 in CAT, the objects are just pair of objects from C and from 2. So we have x cross 0, y cross 1, x cross 1, etc. And the morphisms are a pair of morphisms which are joining the components of each object. For instance, from x cross 0 to y cross 0, we have f, which maps x to y, and identity 0, which maps 0 to 0. And likewise, we have f cross identity 1. And also, we have those identity something of C cross bank, which means just go forward in time. And those are 2 kind of completely unrelated move, and they're independent in a way. C cross 2 is not just any category, it's made of a product of 2 categories, and that ensures that the action on each component is commutative. So those square will always commute. So they also look like the square that we have for natural transformation. So it's very tempting to say, okay, let's build a functor, let's build, and map f cross identity 0 to f of f, identity x cross bank to alpha x, and f cross identity 1 to g of f. So, let's map everything which is 0 related to f, and everything which is 1 related to g, and when we just move bang related to alpha x. So let's look if we can really build a proper functor alpha tilde here. And if we look at in detail to the category C cross 2, we will see that we have 3 kind of morphisms. We have the morphism which don't move in time, they move in C. The one which move diagonally in C and in time, and the other one which are just moving in time 1. And once you're in time 1, there's no way back, so you have only this kind of morphisms. Now we have proposed to map everything 0 related to f something, and everything 1 related to g something, but we have a problem in the middle because we're moving. It doesn't belong either to the time 0 or the time 1. But thanks to the naturality condition of alpha, we can map the 2 different ways that we have to travel from y cross 0 to z cross 1. We can map them in using either convention, seeing them as either a move in time 1, which would map g cross bang to alpha y followed by g of f, or we could see this as first a move in 0 and then a move in time through bang, which would map g cross bang. It would be mapped in D to f of g, then followed by alpha z. So we have defined this the image of g cross bang. Now the question, is it a functor? Does it compose? And we can see that the definition which is given does indeed compose. If we consider the composite travel from x cross 0 to z cross 1, it will be mapped to a similar to the same morphism alpha g compose f, which can also be defined as alpha g compose f of f, because we have this property. Basically, we have this property for natural transformation, and that can also be seen if we consider the composite morphism directly in C cross 2, which go from x cross 0 to z cross 1, and we have two different ways to go from x cross 0 to z cross 1. We can consider this as a move at time 0 or as a move at time 1, and we can apply the same reasoning. And both mapping will be the same morphism in D thanks to the naturality condition, which is just another way of expressing this equation. So we have indeed a proper functor, which you can look at the identity. This is very trivial. It will be always mapped to the identity because we won't move in time, of course, if we are considering the identity in C cross 2. And since f and g are functors, it will automatically be mapped to the identity in D. Now, if we consider the other way, we get given a functor alpha tilde from C cross 2 to D, we can now define f and g as being the composite functor, which maps C to C cross 2 by just tagging along those 0 and then followed by alpha tilde. And then likewise for g, we just tag along each object of C, we tag with a 1, the time 1. And now we're considering this family of morphism in D, alpha, which are just the alpha identity x cross bang for x ranging over the object of C. And it's very easy to see that it defines a natural transformation. And we can see that by just drawing the picture. Because the first mapping from C to C cross 2 will have to commute by the operation which we've done, which are taggings. And this square, which has been drawn, commutes. And now we have a functor. And so a functor maps a commuting square in C cross 2 to a commuting square in D, which means that alpha x is a natural transformation. Now, if we sum up this trip back and forth in cat, so we have this natural transformation alpha from f to g, and we could inject C to C cross 2 and go through alpha tilde. And we have, there's a one-to-one relationship between alpha tilde and alpha. And the side of this, those two triangles on the side do commute. We can define G in terms of the composite, and likewise for F. Now, we've done all this work and we've shown this equivalence, but previously we've shown some similar looking equivalence. Remember we were going to arrow of 2 and then going back through the domain and the codomain functor. And this is not surprising, is because cat, not only does it have product, so it's a Cartesian, it has a Cartesian product, but it's also a closed category, which means that we have this adjunction that go from the set of functors from C cross 2 to D, and the set of functors from C to the functor category D power 2. And D power 2 is equivalent to the arrow category. And so all this construction that we've done, all those proofs, etc., we could have deduced it from the existence of the previous representation of a natural transformation as a functor, which was previously as a functor from C to arrow D. So that's another vision of natural transformation as a drawing. But now, instead of modifying the arrival category, we're modifying the starting point, and we are considering this category C with time, if you want. And this vision of category as mapping of things through time or place or path is is an interesting intuition to have. But that's just one of the many other ways to define a natural transformation. And maybe getting all those different ways will give you a better intuition.